dire bonjour en français quand même. Donc bonjour à toutes et bonjour à tous. Nous avons le plaisir aujourd'hui d'accueillir Ambre Bouillant qui a fait sa thèse au LEDX qui a récliné sur l'effet Frost et qui actuellement est en postdoc à Twente. Et tu vas nous parler de travaux que tu as fait à Twente.
Et en thèse.
Et en thèse, super.
Okay, thanks for this introduction. I'm very glad to be in D'Alembert today to tell you about my research about capillarity and phase change. I will try to cover both the project that I did in my PhD and during my postdoc, but if it goes too fast, feel free to interrupt me. So during my PhD, I have been interested in a very old problem which occurs when we pour a volatile liquid on a very hot plate. For example, here when we pour a water drop on a heated pan, heated at 300 degrees. So in this picture, if you look carefully at the base of the drop, you can see that there is light that goes below the drop, in between the drop and its reflection on the substrate. And this light actually betrays the presence of a vapor film underneath the drop. So this vapor film has different consequences. First, it reduces the thermal exchange with the plate so that the drop can survive for a few minutes to a very high temperature. And it also prevents the contact between the liquid and the plate so that there is no boiling. And the drop has a very minimal friction, so it gets highly mobile. And one of the major results of my PhD was actually to understand better the mobility of those droplets. And to that end, I introduced some tracers within the drop, or onto the drop, and I show here a top view movie of a Leidenfrost drop that is seeded with some surface tracers. And when I play the movie, the first surprise is to see that the drop is animated with very, very strong internal dynamic. We see very fast flows at the surface of the drop. We can follow the motion of each tracer and measure the velocity, and the velocity is typically 5 centimeters per second. So 5 centimeters per second is a huge value. It means that one fluid particle travels 10 times the radius of the drop within 1 second. As this flow takes place, we see some structural organization occurring, emerging. We see the formation of 4 convective cells with symmetry, four convective cells. And I looked at this state from the side. I show here some PIV measurements. So in the median plane of the drop, we can actually see that there are 2 convective cells that are easily visible with some upward flows on the edge at a velocity of a few centimeters per second. So this state preserves actually the symmetry, and we can wonder what is the origin of this flow. I measured actually the temperature profile from side view using an infrared camera, and what we see that the base of the drop is maintained at about 100 degrees, while the top is much cooled down by the ambient air. And this drives actually Marangoni flow at the surface from the hot part to the cold part. And as I was talking to you, actually something happened on the top, and I'm gonna replay this. So if we restart the movie, pretty much just before in this state where we have 4 convective cells, we can see that this flow will not be stable anymore. So here we are attending to a break in symmetry, and spontaneously the drop will start to roll in an eccentric fashion. If I now introduce a laser sheet in the median plane of this drop, I can actually see that there is only one rolling cell left within the drop. So there is a spontaneous break in symmetry. So the drop looks like a liquid wheel, and if I gently deposit it on a hot substrate, and if I hold it with a needle, so we see that the drop rolls, and once it gets released from this needle, the drop self-propels in the rolling intended direction, with an acceleration that is roughly constant. So this result is very surprising because we know that for a wheel to move, it needs to be in contact with the ground. Here the wheel is moving even though it is levitating above the ground. So I have carried out interferometric measurements to resolve the shape of this vapor cushion underneath the drop. And I show here an interferometric pattern. So what we see, when the first thing that we see is that the base of the drop is not flat. There is a hill, and this hill is actually erected by the vapor that tends to rise. So it forms this pocket. But most importantly, we see that this hill is not symmetric. And if I reconstruct the liquid vapor interface along this straight line, we actually see that the base of the drop is actually tilted by an angle. The angle is quite small. It's about a few tenths of milliradian, but still it's quite important. And so everything seems to happen as if the drop were sliding down on an incline plane that they would create themselves. One can wonder if this phenomenon is reproducible. So I reproduce this experiment by looking from the top, and I show here a collection of the trajectory of 100 drops released at rest from at the center of this substrate. And what we see is that the drops do not stay where they are placed. They go in all directions with a roughly constant acceleration. And this isotropy in the trajectory shows us two things. So the first thing is that the rolling axis is completely non-determinist. The drop go in a random direction. And the second thing that it shows is that there is no bias. The drop are not going down on the slope of the substrate. The drop are really able to generate their own motion. So those drops are not simply mobile because of their sensitivity to any perturbation, any disturbance like airflows or slope of the substrate, as it was thought for almost 3 centuries. They are self-propelled. So I'd like now to move to another spontaneous dynamic that I've been studying during my PhD, which occurs for for much larger drops. So we don't see very well. Maybe I can turn the light up. Is it better? Well, not really better, but. Okay, so we restart from a simple experiment where we look at a centimetric drop in a conical trough to keep it in place. And if we look at the drop from above, we see that the drop, initially at rest, will spontaneously get perturbed, disturbed. We see that there are some wrinkles that appear at the surface of the drop and that are axisymmetric. And those wrinkles appear to be evolve within a few seconds to give birth to pulsating stars. So we see here that the drop starts to pulsate at a given frequency. And by plotting, for example, the perimeter of the drop as a function of time, what we see is that as the drop slowly evaporates, there are bursts, there are episodes where the star appear and where we see this extension of the perimeter. And this, So these spontaneous dynamics have been described a long time ago. They were first described 140 years ago. And since there has been a lot of paper published to essentially describe those modes. The frequency of those modes is between 20 and 50 Hz, and it corresponds to the Rayleigh and Long modes that are very well known. And they can actually, star oscillation can actually be excited through different pathways. I mentioned some pathways that have been used in the literature. So depending on the liquid nature, you can excite them mechanically, magnetically, acoustically. And for example, in this case, the author just vibrates the substrate to trigger the Rayleigh and Long mode and to see the star oscillation. But strikingly, in those experiments, in all those cases, we can very clearly identify an external and periodic forcing. However, and in stark contrast, the Leidenfrost star appear even though there is no external forcing, and even though we continuously provide energy to the drop. So I wonder what was the origin of the Leidenfrost stars. And inspired by the experiment of Noblin and et al., I wonder if the vapor cushion was actually vibrating. And to do so, I turn to a much simpler case. I consider a Leidenfrost solid. So for that, I consider dry ice that sublimates at minus 80 degrees without passing through a liquid phase. So just as for the liquid, the dry ice levitates on a cushion of its own vapor, and the thickness of this cushion is actually given by a balance between the body weight and the lubrication pressure associated with the escaping vapor flow. So the higher is the production rate, the thicker is the vapor cushion. So epsilon is actually an increasing function with the temperature of the plate and with the radius of the platelet. So the film thickness can be measured optically. It's 50 micron, it's small, but with magnification lens it is achievable. But vibration would be actually too small to be visible. So I decided to turn to another setup to perform a dynamic weighing experiment. So how? I use a highly sensitive force sensor, and when I place the dry ice platelet on such a substrate, I can actually measure the lubricated force, FL, that I normalize by G to get the effective mass. And what I see, what you can see is that M, the effective mass, is actually an oscillating function with time. We get oscillation with a very high amplitude, about 4 times m naught, the actual mass of the body that can be measured on the cold scale. But what is more striking actually is that the oscillation have a well-defined frequency. This frequency can be read on the Fourier spectrum on the right. It is about 300 Hz. So how to understand this frequency? So I told you that the levitating state reflects a balance between the weight and the lubrication force. If now I perturb this equilibrium, say by approaching the platelet close to the hot plate, then the lubrication pressure or force increases and overpasses the body weight. So the body takes off, and now the lubrication force becomes smaller than the body weight, so it lands back, and this gives rise to a back and forth motion at a frequency that, in analogy with the pendulum system, scale as the square root of G over epsilon, epsilon being the only equilibrium length of the system. So we have verified this formula by repeating the weighing experiment to measure the vapor frequency as a function of epsilon that is varied by changing the temperature of the plate or the body, the platelet, the dry ice dimension. And what we see is that we have a very good agreement between the experimental frequency and this theoretical prediction. So now what happened for water? Let's back to the liquid case. So unfortunately, the weight of the drop is too small for the dynamic weighing experiment to be suitable. So I could not do the same experiment, but we can actually focus at the base of the drop here and show the evolution of a vertical line like this as a function of time. So this gives this typical spatiotemporal diagram on which we see actually that there are some oscillation, vibration at the drop base. We can measure the frequency of those oscillation, of the vapor oscillation, even in the case of water. So here we do not measure SV as a function of epsilon, the vapor film thickness, since it is not uniform. I told you that there is a heel, but we measure it as a function of the drop radius, r, here. And what we find is that SV we can measure SV as a function of r, and it follows qualitatively the scaling that we expect. SV scale as r to the power minus 1/4. So this scaling explains us why this frequency is very sensitive at a small radius, And it also tells us, explains that the frequency gets quite flat for large dwarfs. In the range where stars are observed, in the range of radius where stars are observed, so from 6 to 10 millimeter, we then expect a natural frequency for the vapor that is close to 180 Hz. So if you remember well, I told you that the stars were oscillating at 20 to 50 Hz. So there is a strong mismatch between the vapor film natural frequency and the frequency at which the star appears. So the idea that we had is that perhaps it's a non-linear phenomenon that explains this response, this mismatch. And to understand this mismatch, I took a step back and I tried to look at this oscillation. So I present here two synchronized views, one top view and one side view of the same Leidenfrost drop. And so what we see is that the drop initially at rest will spontaneously get disturbed. So I draw your attention on this view where you see the reflection of the light rim, and you'll see that spontaneously the wave will be excited. So here we see some standing waves that appear at the drop surface. And if we plot now the evolution of this line as a function of time, we see something quite remarkable. We see that the base of the drop vibrates at twice the frequency of the wave. So we have a subharmonic response, and we also have standing waves. So this is reminiscent with the Faraday instability, where we vibrate a liquid bath vertically, and we can excite a standing wave on the bath that oscillates at half the forcing frequency. So here it seems that the vapor excites perpendicularly the vapor field and excites some waves that propagate along the drop and get reflected so as to form a standing wave pattern. Standing wave pattern, so we can anticipate that the response of the drop will be extremely sensitive in one parameter, the size of the drop. And indeed, if I show here 4 movies of the same drop at different times, so the same drop, movies of 4 drops having 4 different radius, and when I play the movie, what we see is that the response gets quantified in the drop radius. The drop gets perturbed only for some very specific values of the radius. So this somehow explains the intermittent nature and episodic nature of this mode. And the resonance condition seems to be actually that the drop enters in resonance when the polar perimeter can accommodate an integer number of wavelengths. Once this first resonance condition is fulfilled, those axisymmetric transient mode can secondarily excite the azimuthal mode, and the lobe, the mode that will be excited is given by the ratio between the azimuthal perimeter divided by the wavelength of the drop. This gives the number of lobes of the star. So we have thus understood the origin of the forcing of Leidenfrost stars and the mechanism by which it can intermittently lock on a specific mode of the drop. It's rather a complex mechanism. So that's all for the part that is dedicated to my result from my PhD. I didn't show some other phenomenon I looked at, but that may actually fuel the discussion of this afternoon. And this also shows the richness of the phenomenon, of Leidenfrost phenomenon, which calls soft matter, capillarity, phase change, hydrodynamic and aerodynamics. And it perhaps also explains why Leidenfrost effect is still being studied 3 centuries after its discovery. I now come to the subject I'm currently studying in postdoc. So after my PhD, I joined the group of Jaco Snoeyer at the University of Twente in the Netherlands. So Jaco is a theoretician. And I looked with Jaco at 2 different topics. First, I looked at a viscoelastic liquid in the context of capillary singularity, for example, coalescence or spreading of polymeric suspension. And I also looked at elastocapillary problem coupled with some phase change, and this is what I will present in the remaining part of this presentation. Okay. So connotation refers to the transition of vapor to a liquid state, and this occurs when we cool down the humid air below the dew point. So when crossing this curve from right to left here, so this triggers the formation of water drops. It can be exploited to collect water in very dry environments, but it can also be very annoying. For example, in this very familiar situation where the humidity collects on your glass and opacify the surface. And the question I asked myself was, what happens when the surface is covered with a very soft gel? How the softness of the gel affects the breast figure or the pattern left by the drop. So why is it relevant? I think for two reasons. The first is that it enables to probe elastocapillary interaction at a very small scale and multiple elastocapillary interaction actually. And it also enables to decrease the roughness of the surface because those gels are smooth at a scale of a few tenths of nanometer. So the experiment I did was to cool down an elastomer in a chamber with controlled humidity here. And I used PDMS elastomer gel, which are prepared by mixing a polymer and a cross-linking agent. By adjusting the ratio between polymer and cross-linking agent, I can actually vary the elastic modulus from 100 Pascal, which corresponds to the elasticity of a yogurt, to about 1 megapascal, which corresponds more to the elasticity of the skin. The soft gel has the remarkable property to be deformed by the presence of the drop. So water exerts traction at the triple line, which results in the formation of this elastocapillary ridge. And the height of this elastocapillary ridge is quantified by the ratio gamma over G. So in my experiment, I vary this length from 0.1 micron for the stiffer gel to about 80 micron for the softer gel. And I show here three different movies. So I'm going to start with the stiffer gel, which is a well-documented case. So if I start the movie, we see that right after cooling, there are about 100 drops that nucleate and start to grow. They start to grow first individually, and then by competing with their neighborhood to absorb the humidity. So there are some interactions that are mediated through air. And then they can also coalesce when they get in contact with their neighborhood. So in the end, the number of drops decreases, and the drop gets bigger and bigger and cover, in the end, about 60% of the surface. I'm going to replay this movie. And because there is another thing I would like you to notice is that there is almost no new nucleation event in the dry spot in between the drop. So now on a softer gel, the behavior is clearly different. So the first thing that we see is that first we generate more and more, more nuclei than in the previous case. And the second thing that we see is that the drop tends to form clusters that exhibit a strong asymmetry. We see a very long cluster, very highly extended. So this cluster can be understood as the following. So the menisci at the gel surface, just as for the cereal floating on your morning breakfast, they tend to attract the drop, and so as to form those clusters. So those clusters, quite surprisingly, show reluctance to coalesce. They seem in contact, but the drop remain separated. So I'm going to start again this movie. So we see that they attract, they form a highly elongated drop, and in the end, it tends to form 2D liquid-like form where we can identify the different droplets. So this results in a very original state in some way, because we form a liquid-like bidimensional form. This behavior is actually validated on an even softer gel, where we generate even more nuclei, and where we end up with this form. So we can actually look at the early stage of the condensation, and we can quantify the number of nuclei that form. So at an early stage of the condensation process, we can count the number of drops and divide it by this surface, and this is what I call N naught. And N naught seems to decrease by 2 orders of magnitude when increasing the gel softness, stiffness, elastic modulus, by 4 orders of magnitude. So it's a very sensitive, there is a strong influence of the elastic modulus of the gel. So Nmax actually reach. So maybe I can show you the plots. So basically, the nuclei density can be counted as a function of time, and what we see is that it reaches a plateau, not really for the stiffer gel, but for the softer gel, it reaches a plateau, and the plateau is actually the value of N naught. That's how I define it. So here we can better see it actually, and after that the drop will start to slowly coalesce. So I have complemented those experiments by looking at 2 asymptotic cases. So first, the case of a pure liquid. So I reproduce those experiments on an uncross-linked gel. So I just use silicone oil. And the density that I found is very close to the value that I found for the softer case. I also looked at the opposite limit, the case of infinite rigidity. How? By grafting some PDMS pseudo brush on a silicone gel. And when I do that, actually, I can measure density, nuclei density that is very close to the stiffer case that we use. So the purpose of that is actually to keep the same chemistry of the surface, but then to have an effectively infinite rigidity. So the first surprise is that the drop density is higher in the liquid case than in the solid case. And since N naught is a measurement of the nucleation probability, it means that it is easier to nucleate on a liquid than on a solid. And to understand that, we can actually compute the energy barrier to nucleate. So this energy barrier actually comes from can be written by writing delta G, which is composed with 2 terms. So the energy that is available due to supersaturation of the vapor. So it's the energy in the vapor phase. And then we also have to add some energy penalty, because when we create interface, we have to there are some additional costs associated to the new interface. And since the shape of the drop is different, whether the drop sits on a stiff substrate, on a solid, or on a liquid, the energy barrier will be indeed different. So I can actually specify a bit of different terms. So the energy available in the air can be written by using some very classical thermodynamics, where we write that the vapor behaves like an ideal gas. And the energy penalties can be written just using some geometry argument and some trigonometry. And so, okay, well, I'm going to pass this calculation, but in the end, what we observe is that the energy barrier can be recast in this shape, both for the solid and for the liquid, where we have a g of theta, weighting function that is in factor of the roll expression, and this function actually accounts for the weighting and the weighting property of the substrate. So we can now measure actually theta and on the different angle, both for the rigid and the liquid case. So I have performed some independent side view experiment to measure the contact angle. So on the solid, I can measure an angle of 108 degrees, while on the liquid, the liquid vapor angle is very low. It's about 38 degrees. So the contact angle of the liquid vapor interface, which is the most expensive interface to create, is markedly reduced on a liquid, and so as the energy barrier. So I plot here delta G normalized by kT as a function of R. In blue you have the liquid case, in red you have the solid case, and what you see is that the amplitude of this bump is smaller in the liquid case than in the thicker case, so the energy barrier is indeed lower down on the liquid. There is another thing that you can perhaps see here. Maybe I can. So since the energy barrier is smaller in the liquid, the probability of nucleating drop, which is a Boltzmannian function, will be actually higher on the liquid. And one thing that you can see on this plot is that the radius, the minimum stable radius above which the drop can form, is actually smaller in the liquid case, which may actually explain also, which can be visible actually on those breast figure on the top. Okay, the second thing that is that we can notice is that remarkably, once a first batch of droplets has nucleated, there is almost no new nucleation event. And together with Bruno Andreotti, we have shown that this can be ascribed to the depletion of vapor at the vicinity of the drop. So around the drop, the humidity will be consumed, so there is a vapor content phi that is lower. And since phi intervenes also in delta G star, in the energy barrier, it will completely quenches the probability of nucleating a new event. Last thing that we can comment on the early stage of the nucleation is that N naught varies continuously with the elasticity between the liquid and the rigid case. And this arises from the fact that the elasticity continuously adjusts the shape of the drop between that of a spherical cap that meets its substrate with theta, the Young contact angle, to that of a floating length here. And so because of this continuous change in shape, it will continuously modulate the energy barrier. So then we can actually look at the later stage of the condensation process. So from left to right, it's still I increase the softness of the substrate, and from top to bottom, time goes on. And what we see is that at a later time, the coalescence is hindered, and we have tried to understand this by doing some complementary experiment, but it's still an open question. So to account for this resistance to coalescence, we have drawn two scenarios. So the first may be due to the migration of free chain of PDMS at the drop surface. So because of this cloaking layer, then when two drops get in contact together, it takes some time for this thin film to get thinner and thinner. So this is an effect that has been studied here in D'Alembert. And the second scenario would be due to some viscoelastic braking effect. So because those elastic capillary ridge are singularities, it is extremely energy consuming to move them, and so the gel has to dissipate energy during the approach, and so the approach will be much slowed down. And in order to discriminate one scenario compared to the other, I run a certain number of tests, experimental tests. So the first was to check the reversibility of the experiment. If I stop the driving force for condensation, so if I stop cooling the substrate, the drop actually evaporates in a time that is very comparable to the time that it took to form them. So it seems that this is more in favor of scenario 2, because the evaporation will be a bit slowed down because of this oil layer at the drop surface. I also decided to follow the procedure, the cleaning procedure that Aurélie developed. So I just took the gel. They were swollen during 1 week in toluene, and then deswollen in a bad solvent, ethanol. And then after evaporating the solvent, you end up with elastic matrix that is that doesn't have any free chain in it. And if I do the same experiment, and I show if I do the same experiment on the clean gel, I show here in this insert the associated graph figure. We can see first that the result for the initial number of drops isn't changed, so that's first good news, let's say. And but what we see, and that is quite remarkable, is that the coalescence is quasi-instantaneous. So we suppress the delay in coalescence, so it's more in favor of scenario 1. So can we conclude that the delay is due to migration of free chain? This is a bit more complex actually, because by removing also the free chain, we also affect a lot the deformability of the substrate and the viscoelastic properties of the gel. So the drop will have a different shape. And perhaps one proof of that is that we see that the drops are not circular anymore, so there are some pinning in the drop at the contact line. And to perhaps conclude, I can show here a top view movie of two small drops that are placed on this gel and on a regular gel. And so we see that because of the carrier's attraction, they will attract and eventually coalesce, spoiling alert. But what we will see, and I'm gonna speed up the movie because it's a half an hour movie, we can see that the drop will get attracted, but in a non-monotonic way, meaning that the attractive force is more intense in between the two drops, I mean, where the separating distance is minimized. And so this leads to the formation of a pointy shape of the drop. I don't know if it's visible now, but in the end we can see it. You can see it clearly that the drops are not circular anymore. There is a pointy shape here, and perhaps also the delay in coalescence could be due to the fact that this attractive force is very intense in where the separation distance is small, but the remaining part of the drop creates some inertia and prevents the drop from moving toward the other. Well, this is an open question, as you see, and with this I would like to thank you for your attention, and I take questions.
Thank you very much. Questions? Boom. No question?
Is there anything you can say on the first part of your talk? Is there anything you can say about the substrate? You didn't mention anything about it. Like, did you change the shape or the first part, the Leidenfrost drop?
Leidenfrost, yes. So I actually used different techniques to get the drop in place. So it was either on a flat plate with a needle, just a capillary trap. But I also took some conical trap or some parabolic trap. I played a bit on that. I also tested what happened on the rough substrate. So for the self-propulsion, for example, the self-propulsion is observed even on a very rough substrate. And if you do also the experiment, I don't know exactly on which part maybe you're
Just
not
on the self-propulsion, for example.
Yes, okay. I also did the self-propulsion on a parabolic trap because then you have a constant thing. You can actually infer from the position of the drop what is the tilt at their base. So I tried to do that, and you can see that the drop self-propel even in conical or parabolic trap.
Yes, so you have shown contact line on elastic surfaces. So it's an interesting topic that has been at the center of some controversy between Andreotti and Lima and others. Do you have any opinion on this controversy, or do you performed any experiments that could help solve the controversy? Does Jaakko Neuer has any opinion on it?
definitely have as an opinion on that. So you're probably mentioning about when thinking about the shuttleworth effect. So my experiment, so it means that the contact angle and the surface tension will change upon stretching of the substrate. In my case, I did not stretch the substrate, so I did not consider in this context the Shuttleworth effect, and I didn't do any experiment to solve this controversy.
Okay.
Sorry?
Sébastien,
Quel est le temps de coalescence à la fin? Ça collapse en combien de temps? Une dernière microseconde ou
Non, pour la fin?
Oui.
Alors pour des gouttes individuelles, je les place avec une distance, une séparation qui est fixe. Ça prend de 5 à 1 heure pour vraiment coalescer. Mais en fait, l'approche, la vitesse, elle n'est pas du tout monotone. Donc au début, c'est très lent comme approche. Et puis en fait, d'un coup, ça donne...
Combien de temps le d'un coup?
C'est pas une vitesse constante, je dirais que ça prend, ça prend peut-être moins d'une seconde.
Ça dépend de la viscosité, de la taille du bout?
Ça dépend, mais en fait j'ai l'impression que avec là ici je prends une image toutes les 5 secondes, donc déjà ma résolution ne serait pas suffisante pour observer ça. Mais ça apparaît vraiment d'un coup, il n'y a pas de retard à la connaissance au moment où les deux gouttes se touchent en fait. C'est pas comme si, en tout cas quand on regarde ça, on a l'impression qu'il n'y a pas vraiment ce film qui a besoin d'être aminci pour permettre la connaissance.
Ok, super, bon, ben, merci beaucoup.